Howdy everyone, and welcome to the last scheduled Drones in Agricultural module. This is module 3, and it will be about processing all of the data that we collected in module 2. Before we get into that, I just wanted to show you an output that I made recently. A postdoc in the weed science department was doing a study on barley, and they're doing an agricultural extension publication, and they wanted some more visuals so that they could describe what was happening in their trials. So I got to go out and fly a drone for them, and we can zoom in and see the individual plants in the individual fields for each trial. I was really happy with the output, and it should hopefully end up in a publication sometime soon. I made a nice map out of this too with individual trial boxes, but this is all done out of a Phantom 4. Has about 127 photos all stitched together. And I think it really helps explain which one of these is which field trial. So let's get on to see how we can make one of these. Normally, I like to start these with a objective slide, but since we're doing a lot of data processing, I think more or less a flow chart helps. So we start with our inputs. So we have our drone photos and our GPS points from the corners of the fields, as well as the GPS targets. And what we're kind of aiming to get out of here is to answer the question that I asked in the field of which one's greener, which one has less soil showing. And then we also want a classified shape file that we can feed into a tractor. So how do we get from data to these two outputs? So step one, we color correct the photos so that they look even, and I'll show you a little bit more in detail all of this. Then we will stitch together the photos. Then we'll take the GPS points that we got and turn them into spatial points and polygons, little bounding boxes around our fields. Then we will make sure that the images that we took are stretched on a globe properly with georectification. From there, we'll clip out the individual sections of the farm fields that we want with the polygons. We can do zonal statistics, and also we'll calculate our NDVI values from in the previous step, and that will hopefully answer a question of which one is greener and has less soil coverage. And then from that clipped and calculated NDVI, we can classify those values and output a shape file after we vectorize it. And it sounds very complicated, but it's all very simple. And as long as we follow the flow chart, we can always get an output. So here we'll go on to step one. So step one, we'll start just getting our data into a computer system. So we'll start just with the drone photos and then the GPS stuff. So we take the SD card out of the drone, or it can download to your phone, or you can plug your drone directly into your computer. It navigates just like any camera. You get these marked DJI photos that you need that are of your entire survey. I usually like to just put these in a separate folder for the individual project that I'm working on, and then deleting them off of the SD card and putting it back into the drone immediately. I also like to make sure that we have all of the photos here and that they look good. And if there's any that are really obviously bad, I like to delete them after I've copied them over. So that's the photos. Now let's go to the GPS points. I'm going to kind of cheat here. So here's the final stitch together imagery. And I want to show you what the GPS points look like. So here are our control targets, the points of them that I've read off of a GPS unit, and then I get those out of an Excel spreadsheet and I load them into ArcGIS, or in this case, I put them into Google Earth so we can know roughly where they are. And then I did the same thing for the corners of each field that I took for the right field and the left field. So the right field in this case will be the native vegetation, and the left field will be the oats or barley or whatever the crop was growing there. So back to our flow chart, we can cross off that we got all of our data in. So we have our points and we have our photos. So let's go on to the color correction step. What that means is if you don't do this and you stitch them all together, it might be kind of hard to see, but there's this big yellow patch in this photo. And the reason that happens is that this takes a bunch of time to fly, maybe 10 minutes. And if a cloud flies over the sun and then back over, you'll have a very blue photo and then something that's a bit warmer as there's less sun for a brief minute or there's more sun. And the DJI you can set to have a fixed color balance, which means that it just keeps taking photos over time at the exact same calibration. And if you do that, you can adjust it later so that all of these photos will be the same color no matter what the sun is doing. To do this on other equipment, such as the NDVI cameras, the multispectral cameras, they actually have a sensor above the drone that measures the change of the sun. So it does these kind of color calibrations on the fly. So we're going to for our drone photos, we're going to color correct for these yellow splotches today. To do that, we'll be using an old free program called ImageJ. You can use just about anything else than ImageJ. It is a free program developed by the US government and is a back end to do image processing in like laboratories and microscopes and stuff like that. And it's a very old program, and it just looks like this one box, and it opens up something, a different box every time you open up a new photo. And it's really good for examples. I usually use for just my own processing a very old version of Photoshop. It allows you to automate all of this, and it is an extremely small program modernly, and it does automatic white balancing that you can apply to a whole folder. And it's very consistent. That's what I used for the photo that I showed you at the start of this module. But if you're doing this professionally, you might want to look into newer versions of Photoshop or any other kind of color calibration techniques. I know that Agisoft does have something that can do it on the inside of its program, but Photoshop for me is something that I've always worked with, and I could implement it a bit faster. Speaking of Photoshop, I have slightly edited this photo. It's extremely contrasty, and I'm going to show it as how we color calibrate it. So we want to make it consistent for today, and we want to make it consistent for any other future studies. So what we really want to do is bring out something that is white and black in the field that will be the exact same color when we go out next time. That way we can tell the colors that are in the field one day are comparable to the colors that are in field 2 weeks ago. I completely forgot to bring out a color calibration tarp. So we're going to have to use something that is white and black in the field and is perpendicular to the sun, doesn't have too much of a highlight, too much of a low light. And what that actually turns out to be are the ground control points that I set out earlier. So if we zoom in on the ground control point, I can hover my mouse over these white pixels, and you'll see that the values here are in red, or up here. These are for the highlights. The maximum value that red, green, blue photos cameras can have, or at least most of them, are in between 0 and 255. 255 is the maximum, which means that it is closer to white, so black to white. These values here always follow RGB, red, green, blue. So we can see for a couple of pixels here that it is at 251 and in red and 255 maximum in blue, or green in green, and B would be the blue is slightly lower than it should be. So we can actually correct this in the image J, and this is how white balancing works, by reducing here the maximum value to the number that we read here. So it will decrease what the screen is showing as white. So effectively, it will make anything that wasn't showing up as white, white. And you do the exact opposite for black. It's kind of confusing, but there's a bunch of other better ways to do it than with image J. And what that does is make sure after you did all of that processing that the colors are consistent, and this is roughly what you'd see, that it's not tinted yellow, it's not tinted blue, it's not overly contrasted, it's just white and black, and it's going to be the consistent color of like what you would be seeing out in the field. So back to our flowchart, that's color correction. And now it looks like we're going to get to stitch things together. How I do that is with a program called Agisoft. If you're interested in starting your own business, the business license for this program is a one-time fee of $180. That seems a little expensive, but the drones are a lot more expensive. This software just works really well, and my friends who are in the drone modeling kind of fields, people who work with Esri, who make the ArcGIS software, they use this type of modeling software. So what it does is, here, this is me opening up the program itself, and I load in all of the photos. The program itself can read the metadata of the photos and know exactly where that photo was taken in space. So the drone tags it with X, Y, and Z coordinates, and also tells the program that not only was it taken here, but the camera was at this pitch, roll, and yaw. Once that's done, once all of those photos are loaded in, the program looks for corresponding pixels that are exactly the same where it would expect. This is called a sparse point cloud. It is the very beginnings of a three-dimensional model. And from that, once it gets all of these photos aligned, and you can run the next step, which is called building a dense point cloud. So this looks pretty good. This is just compiling all of similar points that are within individual photos, and it can guess roughly the height of each of these pixels. From there, we run the next step, which is a mesh. And this is, so this is a mesh. It's not as clean. It doesn't use very many faces, but it basically draws lines from the individual pixels and then colors in all of the area in between them. This is now something that is like a true three-dimensional model that can be either 3D printed or put into a video game almost directly. This would, of course, need cleaned up, but it's something that is usable outside of agriculture and academia. You can just make 3D models instantly with drones. And then finally, you run something called an orthomosaic. So it clips the photos and stitches them all together automatically. To do this for this field with 54 photos took a matter of 15 to 20 minutes for the program to run in its entirety. Usually I estimate about an hour for small projects like this. This is exportable as something called a GeoTIFF, a TIFF file being a type of image. And the geo tagged on it is that we know where this is in space. So this can be loaded directly into Google Earth or any QGIS program. And the program outputs which way is north, which is helpful, but doesn't really give you a scale bar. So you can do that in any sort of map making program. So now that we got our GeoTIFF and we stitched all the photos together, let's bring in the spatial points and polygons and process them in QGIS. So there is different software suites. ArcGIS is the professional one that you may have heard of. It's used with the government, and it makes maps. It's extremely powerful, and if you wanted to go into the geography department, you can basically get a master's degree just using that program. There is an alternative of that, which is free. It's made by a lot of enthusiasts of the other program, and usually when something new is on the scene, QGIS has that tool first, and it is eventually brought into ArcGIS. So I'll be using QGIS, and you can use it free if you want to in the future. So it looks like this, and I take that GeoTIFF that we made, and I put it in QGIS. Let's get our points in here. So loading the points that we saw earlier into QGIS, we can overlay them on this image and see where they are. Here we can see the bounding corners of the fields, and we want to turn this into a polygon. To do that, we run a bounding box around that in QGIS, and it just makes a square around the individual points. One of the issues is that I measured the plants that were on this row here, these 2 or 3 rows, and we can see that it's off when it gets to the end. So if we go back to the last module, and you saw that box that was a little off or squished or something, this is exactly what I would be looking at in the data. So it's off just by a bit. We're not looking at the correct plants, and we want to start to do the geo correction to shift this back over. And that's why we got the ground control points. But we've loaded our spatial points in, and we've got our spatial polygons. So we can cross those off. And like I was saying, let's go to the georectification step. If we zoom in on the photos, on the geotiff and the spatial points at the same time, we can notice that the geotiff and the spatial points are slightly off. And we need to stretch the image so that it fits, that these red dots are exactly over the centers of these ground control points. To do that, we go into the georeferencer. Let's see if it highlights. Yes, it does. The georeferencer tool in QGIS, and it will pull up a separate window. It'll just pull up the one map, and we'll start adding points. So you zoom into your target, and you hit the play button so that you start adding a point. It will pull up this box here. You'll click the From Map Canvas button, and you'll click right here. So instead of using this box, you'll use this box here, or you can just type in from your GPS coordinates the numbers here, but I find it easier to load them in and then just click where they are. After that, it adds one point here, and it gives you residuals. So how far away was it? But once you, so it lets you know that you've put your point here, right in the center, and you've clicked the other spot. The residuals, if you keep adding them, will tell you kind of the error of the best it can stretch it, and how many pixels is it off. That's really important for these fine grain photos where you if you're 1 centimeter off, you might be, you're not looking at the exact same pixel. But in this case, I'm not going to do those sorts of calculations. But going from our original bounding box, after we hit play and do that for every one of the targets, the computer program restretches the image and it lines up perfectly, just what we wanted. It's nice when technology works. So now we can, and that is just done to the geotiff itself, not to the bounding boxes or the spatial data points. It is only done to the images that we got from the drone. Done with georectification. Now we'll clip and calculate our NDVI values. So we have our 2 boxes. I didn't load both of them in, but we have our 2 boxes, and we're just going to go into QGIS and run a clip tool. This is just for the native vegetation. So it does this one at a time. It clips it, and kind of like in Photoshop or anything else, it just only retains the pixels that were underneath that bounding box. From there, we can go back to where we were doing the georeferencer and do Raster Calculator. A raster is an image that refer to individual square pixels. They don't need to be square, so that's why they're called raster rather than pixels. The other type is vector, and if you're big into graphic design, vectors are mathematic lines that can be blown up infinitely. And unfortunately for us, shape files are vectors, which are good for some calculations, but that means we're going to have to eventually turn our pixels into these mathematic lines. Not as scary as it sounds. There's just one tool that does that. We'll get to that in a second. But the raster calculator can take the values for each individual pixel with inside of it and then read the red, green, and blue color bands and calculate something. So if you're doing multispectral, it could calculate NDVI, or in this case, we're going to do the false NDVI. Each of the layers that have been clipped have 4 associated bands with them, the red, green, and blue, and then the last one is just value, and that's just making sure that they're in order. So we can completely ignore number 4, and we want to work with red and green, so 1 and 2. So we can write out, after clicking on the individual boxes here, our NDVI formula. And after looking at this, and I'm not going to look at it too closely, I think I've slightly messed it up. Yeah, because this isn't the highest value, but just the kind of normalized value. So it's close enough for an example. But what this will now do is output an NDVI value, just one band for all of our pixels for one bounding box. And we've now done it for both of the bounding boxes, and these are our NDVI photos. So the red ones mean there's more red and less green. The white shows that there's almost no green, and the very green and darker green pixels show that there's a lot more green. These are the plant tops, the greenest and healthiest of leaves. So that's our clipping and the calculation of the NDVI. Let's do some zonal statistics. And statistics are always scary, but we won't get into it too much. And it's all, again, one little tool within QGIS. So we can just look. I don't know why minimum pulled this up, but you can do zonal statistics is what you'll look for, and you'll run it on each of the bounding boxes, or each of the areas that you're trying to compare together. And that's our zonal statistics. And now we can open up those little web pages and help answer our question. So our question is, which area has more green in it and less soil? So we're going to say that is correlation with a thicker crop and less bare patches of soil. And hopefully that's better for a cover crop for the winter. How this would be expressed in the data is that there would be more green pixels, or on average, the number of pixels would be closer to 1, or higher would be greener. So the higher the value, the greener something is. So if we look at our mean value of the right field, which is the mean value, which is the right field, which is the native vegetation, it has a mean value for all of the pixels of 0.166. And if we look at the values of the barley field, it has a mean value of 1.84. That's higher, but there is some standard deviation, which means that they're comparable. But if you just had to ask the question of which one is better, the mean value of the barley is higher. There is less soil present. So I would say that the barley was a better cover crop, just density-wise, and not showing as much soil. And that answers our question. Next, we want a classified and vectorized output. To visualize these colors here, normally what we would see if I just loaded this into QGIS is it go from the lowest value to the which would be black, to the highest value, which would be white. Very similar to the like image J. If we only had one band, we would just go from black to white. So what we want to do is classification, but I've already done that to even do this visualization. So here red is lower, green is higher. I did that with the symbology of the layer in QGIS, but we would actually have to calculate it so that when it reads into a tractor, it's not, negative 0.05, but just number 1, and then section number 2, section number 3. And without getting into it too much, you can easily do that in the raster calculator again. In the raster calculator, to do this classification step, what you would do is say every pixel has at least 1. Then if that pixel is over 0, meaning that there's more green than not, add 1. Then after that, you can do your highest step of saying if it's over our mean value of 0.18, add another 1. And that successfully classifies your image. So something that your tractor can just say, for class number 1, we apply pesticides. Class number 2, we apply half as many pesticides. In class number 3, do not apply any pesticides. And the output kind of looks like this. This is still a raster. So we need to run a vectorization on it. And it's just another tool that's called vectorization, raster to vector. And what that does is it makes each line in between each of the pixels a mathematic line that you can zoom into infinitely. It's still classified exactly the same, but is now ready to be exported as a shape file. So we did our classification and vectorization. And now let me show you the final step of exporting a shape file. All you have to do is click on that layer of that one polygon that you've classified. And here we can see the individual classes of 1, 2, and 3, and 0 if need be. We right click it, we click export and save features as. This then save vector layer as Esri shapefile. You just name it, you hit OK, and that exports your shapefile, and that's ready to be fed into a tractor. And that is down to the centimeter pixel for our DGI photos. So you might want to upsize it a bit or fly it a bit higher and to feed it into your tractor, depending on how accurate that tractor can spray. But if there was a bug on a leaf, your drone might have been able to identify it and your tractor might be able to spray it. So that's the new advances in precision agriculture. But that gets our shape file as an output, and we've answered a question. And we're done. So that was all 3 modules. It went from the history of drones and let you think about what questions you can answer with our paper review. And it went from just an idea to data collection to how you process that to feed it into a precision agricultural tractor. Boy, isn't that neat? I'm just so excited. So I hope you guys found that interesting. I don't have a conclusion slide here. I felt like that I was about 50 slides for me to make. I hope that was enough information. I did at the end skip over a bit how the things were classified. if you guys have any questions in the future about this, I'd love to talk to you about how this is all done. If you have more of an interest about how to operate QGIS, I always encourage the geography department. A couple of their ArcGIS classes are really valuable in this field. So with that, I might be creating a small quiz. We'll see, and we'll see if Dr. Edgar needs me to make any additional modules. However, this is the last plan one, and I am also making a drone club on campus. So if you guys would like to join and maybe get some hands-on experience in the field with some drones, we can go find people who have ag fields that they want to get photos of, and eventually into a publication, and I can show you all of this hands-on from out in the field to processing for our individual projects. So with that, thank you for watching all of my videos, and I hope you have a good day, and I hope you have a good rest of your agricultural classes.